So this is the last example of the whole course, I think. So let's give it a go. So we've got a car, the math, 750 kilograms, going down a slope incline at 10 degrees, traveling at 6 meters per second. Driver jams on the brakes and causes all four wheels to lock. So we're going to figure out how far the tires will skid on the road. And it's given us the kinetic coefficient of friction. So let's have a think about, we need a free body diagram first. I've stolen this one from the textbook, save me redrawing it. But we've got mg acting on the car, so gravity acting on the car, 1750 times 9.81 newtons down the way. Then we're going to have a frictional force with the car with its brakes locked on. We're going to have a normal force reacting to the vertical components. And so we do also have to think about the fact that this force here, so that weight, we're probably going to have to, well, not probably, we are going to need to split that up into its vertical component and its horizontal component, like so. It's going to be too long, but it's okay. So let's call this, we've got that as FA. I wonder why they chose A, because it's car A, I guess. And we'll call this, I don't know, WX, WY, just for the weight. First things first, let's figure out those components first. So WX is equal to mg, so this is 10 degrees in here, WX would be up here, and so it's going to be sine mg sine 10 degrees, which is equal to, the mass was 1750 times 9.81 times sine 10, which is equal to 1750 times 9.81 times sine 10. That's 2981. Yeah. Yep. 2981 newtons, because this here is 1750 kilograms, and so you're going to times it by roughly 10, so that makes sense. Sine 10, let me just check that, yep. Then we've got WY is equal to mg cos 10 degrees, which is 1750 times 9.81 times cos 10, which is equal to 1750 times 9.81 times cos 10 is equal to, we might just start doing these in kilonewtons, so that's 2.981 kilonewtons. This one ends up being 16.91 kilonewtons. In the y direction, 1.6 ton. This was one, yep, that makes sense. What else do we need? So now we need to figure out that force due to friction. So they've called it FA, let's just use that. FA is equal to kinetic coefficient of friction times the normal force. Now we haven't really figured out the normal force. NA is just going to be equal to the only vertical forces, or the only component that's perpendicular to that slope to give you this normal force is that component of the weight. So that's just going to be equal to WY, which is equal to 16.21 kilonewtons. So therefore that's equal to, I think the coefficient of friction was 0.5, which is pretty high. It's a high assumption for coefficient of friction, times 16.21. Must have good tires, this car. So therefore that is equal to 0.5 times 16.21, 8.105 kilonewtons. So then I think we're pretty much at the stage where we can write down the work energy equation. So sum of the work done is equal to half change in kinetic energy, half m V naught squared minus, change in kinetic energy, so it's the final, take away the beginning, V1 squared minus V naught squared. Now let's figure out what forces are doing work. So the car's going in this direction, down the slope, so the normal component of the weight is not doing any work. The horizontal component of the weight is doing work, it's doing positive work, it's in the same direction. And the coefficient of friction is doing negative work, it's in the opposite direction from the direction it's moving in. So let's just figure all those out. And so we're going to have positive Wx times, what are we going to call that down the slope? Let's just go, they're calling it S, so let's stick with that, times S. And then, so we've got S positive this way, and W is in that direction as well. So then we're going to have minus FA times S, because FA is in the negative direction, opposite from the direction the car is going in, and that's all we've got. No other forces in that direction. Is going to be equal to a half times. Now we have to be a bit careful here. If we're going to use kilonewtons here, then we need to be using tons for this, or we could change these back to newtons. I'm just going to change this to tons. So 1.75. So when you're using kilonewtons, you want to use tons for the mass, wasn't it? 1.75 tons, 1750 kilograms. V naught, so V1 is going to be 0. And so, because we want it to come to rest, and V naught, they told us, was 6 meters per second times 6 squared. Let's start putting some other numbers in here. So that means, so we already figured out Wx, so it's 2.981 kilonewtons times S minus 16 point, FA was 8.105. 8.105 times S is equal to, let's figure out what that is, 0.5 times 1.75 times 6 squared, 31.5. Now, have to be a little bit more careful. So let's take away the initial velocity, so minus V naught squared. So what was going to end up happening there was S was going to be negative, and I know S is not negative. So going back to figure out what I've forgotten, so it's half m V1 squared minus V naught squared. So it's V naught that's got a value, it's the one that's 6. And so it should be, this should all be negative, negative, negative. Then we're going to work out positive. So then that is going to end up being 8.105 minus 8.105 minus 2.981, because we can multiply both sides by -1, so we get 5.124 S is equal to 31.5, so S is equal to 31.5 divided by that is 6.15, 6.147, but 6.15 meters. Just check that, and I've made an error in there. This should be 16.91. Not sure how I made that error, so let me just fix that. That should be 16.91. This should be also 16.91. Last example, got to make a mistake. We've got 0.5 times 16.91. So that's going to end up being 8.455. What else does it change? So this is also 8.455. This ends up being 2.981. Is equal to 5.474. And so that displacement ends up being 5.75 meters. 5.7. Okay, so the car is going to take 5.75 meters to stop. Right, that's us all done. So what you'll have noticed is, again, this one could have quite easily been done with kinetics and equations of motion. You'll notice that this type of problem, it's the ones you're solving with energy are always the ones that are talking about what happens between velocity and distance. And then you'll usually be using the work energy equation as one way of solving them. Or you could use, it's generally the ones that you would have ended up solving with v squared s is equal to v naught squared plus 2a s minus s naught. And so it's the problems that you would solve with this equation can also be solved using energy. The other time you use energy is if another part of the question is asking you for the energy at a specific point, something like that. And like the last example we did, for these ones where there's some kind of curve or something like that, it'd be pretty hard to apply the kinetics that we've learned to that type of problem, and so you probably want to use the energy equations for those as well. Okay, that's it. Last example. Thank you very much for sticking with me through this course, and good luck with the exam when you get to it. And yeah, good luck with your careers as well, with whatever you do next. It's been a great pleasure to teach you all. See you in class.